Can we predict fluid flow turbulence from first principles? Imagine trying to forecast a storm's exact path and strength just by knowing the basic weather rules. That's similar to predicting turbulence in fluid flows from first principles. It sounds straightforward, but it's actually very complex. The main equations that describe how fluids move are called the Navier-Stokes equations. These equations account for forces like pressure, viscosity, and momentum. If we could solve these equations exactly, we could predict when and how turbulence happens. But here's the catch. Turbulence is chaotic and involves many scales of motion, from large swirling eddies to tiny dissipative vortices. Solving the Navier-Stokes equations for real-world flows with all these details is practically impossible with current computers. In fluid mechanics, we classify flow regimes based on the Reynolds number, which compares inertial forces to viscous forces. When the Reynolds number is low, the flow is smooth and orderly, called laminar. When it's high, the flow turns chaotic and irregular, which we call turbulent. The Reynolds number helps us predict when flow might become turbulent, but it doesn't tell us exactly how turbulence will behave once it starts. It's more like a warning sign than a full prediction. Turbulence arises because of instabilities in the flow and nonlinear interactions. These cause energy to transfer across different scales, from large to small. The Navier-Stokes equations do describe these processes, but solving them directly for turbulent flows is extremely difficult. Direct numerical simulation, which solves these equations without any approximations, requires enormous computational power, often beyond what's available for practical engineering problems. To get around this, engineers use turbulence models that simplify the problem. These models are based on averaging the flow properties or filtering out small scales. For example, Reynolds averaged Navier-Stokes models use statistical averages, while large eddy simulation models focus on large structures and approximate smaller ones. These models relying on assumptions and empirical data, so they are not pure first principles. They give us useful predictions, but are not exact solutions from the fundamental equations alone. Recently, scientists are working on more physics-based models that connect turbulence behavior directly to measurable quantities like velocity gradients and momentum transfer. These models aim to improve accuracy without relying heavily on empirical tuning. Additionally, machine learning techniques are being explored to predict turbulence by learning patterns from detailed simulations or experimental data. These methods can capture the complex dynamics better but still complement the fundamental physics rather than replace it. In practical engineering, predicting the onset of turbulence and its effects is vital. For example, designing piping systems, aircraft wings, or heat exchangers depends on understanding flow regimes. The Reynolds number remains a key tool because it helps scale laboratory results to real systems. Turbulence models integrated into computational fluid dynamics software allow engineers to simulate turbulent flows with reasonable confidence, even if they are not perfect predictions from first principles. In summary, while the fundamental physics equations are known, predicting turbulence directly from first principles is not feasible for most real-world situations today. The complexity and computational demands are too high. Instead, we combine theoretical understanding, empirical models, and modern data-driven techniques to analyze and predict turbulent flows effectively.